If you're watching online, this is the start of the afternoon session. We're going to watch how to discover weird new particles, emerging quantum quasi-particles on minute physics. I'm going to pause the recording now to show that. All right, so what we're going to do now is we're going to look at your student work. So I'm going to pass out, or if someone can help me pass out this student work analysis sheet. Yeah, one for each person. And if there's not student work at your table, it looks like we have a lot of student work. So if you can, does any table not have any student work at their table? Because there's people that brought a lot to share, so that's good. So, yeah, well, welcome, Rolando. And I'm going to pull up some digital copies of student work that was shared. So, pick. If you have a table with more than 4 pieces of student work, pick 4 pieces to look at, however you want to, or one for each person. And look at them, keeping in mind the algebraic thinking. I'm going to pull up some instructions right now, too. So, let me pause the recording. So I can pull this stuff up. So I'm going to pull up student work like this page for you watching digitally, but the instructions are to think about it in terms of this. So this is the instruction for your discussion. It's, each person chooses one of the pieces he or she brought to the group, presents briefly an explanation of why you brought it. After each presentation, the group members can comment on what they wrote about the piece on the student work analysis sheet. What evidence do you see in these papers of the building rules? Well, just think about all the algebraic habits of mind, because this was specific to one that was building rules represent functions. So think about how do students organize information, in what ways they describe the rules they're building, and other questions about their algebraic thinking. But this rules were directly related to the staircase problem, not the ones that you have. But we have 3 different problems out there. So present why you picked it to your group. Look at it. Fill in the analyzing student work sheet. And then talk about the what evidence you saw of their algebraic thinking on the paper. So I'm gonna start with so I'm going to start sharing stuff digitally now with other people. So for those watching digitally, If you're watching digitally, I forgot to turn on the microphone, so you just saw a bunch of video without sound. But what I was sharing, if you go back, was students' work. And you're thinking about discussion questions of what algebraic thinking that the students had in mind, what evidence you noticed of algebraic thinking, your interpretation of what this evidence means, and alternative interpretation or possible meaning. So looking at the students' work that I had just showed. So this was a crossing the river problem.
It's amazing. Teacher from Van Horn went up and replicated the project with her kids in Van Horn.
Okay, so we're going to go back from discussion now.
We took the names, dates, every bit of information we could get. We took digital photographs. The more advanced versions of it, we actually have taken GPS markers so we can mark where every record came from. So you can see geographically how the graves are related if you wanted to. Great for middle school statistics.
When we went to
anyone have anything? So I got a couple examples from some people.
What
Here we go. Let's see.
like that. I was having geography. We were doing circumstances. So I explained that
an example.
A new university, but it has to be equidistant to Fort Davis, Alpha, and Marfa. So we wanted to find that place where to put it. And I print just a map of all these places, and then we work with compasses.
Of crossing the river. And
we found the.
this one was shared.
That's a great idea.
The group who shared it,
And I didn't do it.
explain why they shared it. So,
But we could
did you think
other tools.
algebraic thinking.
But I mean, we created a triangle, and then we used some instructions, and then we found the precise point so that everybody will
Have the same distance to travel.
will drive the same distance.
I'm going to steal that idea. I'm teaching geometry right now, and we'll be doing Circum Center in a couple of weeks. And I'm going to steal that idea about how could we locate UTPB to be one university, and I'll just pick 3 towns and say, you know, they shouldn't have put it in Odessa. They should have found a place that was equidistant, not just between Odessa and Midland, but. And then maybe they'll move our university. Let me see what he's got going here.
And then I got another one shared.
Okay.
The second page of the postage stamp problem.
And doing it actually with compass and straight edge is probably better for kids that have never done compass and straight edge much. That's a good use of not using the technology.
I had never think of that. I had used the Google Maps as well for different activities, but it's way simpler than that. There was, I don't know if you remember, but back in the day when they had Cisco, there was a lesson, actually this lesson, the crossing the river, is from Cisco. Yeah. It was part of the other one curriculum of Cisco. Well, there was another one called Miles Intersection. And
what grade?
Data collection and how
pre-calculus
going to be regulated, right? And,
so does anyone else
what they had to do was to estimate how many blocks away, or not how many blocks away, how many intersections on street they would have from home to school. And then they would estimate the distance from home to school. Well, I had them do that, but I would have Google Maps, and I would zoom it in such a way that they could actually see their house and the school. And then there, they could actually count the intersections looking at the map.
Well, you made a
Google Maps has a chart with the real line, the distance, and with the
one written thing.
or it tells you 1 inch is, or this much is 500 feet, or 1 mile, or whatever, depending on the zoom.
You know, if you open it in Google Earth, they actually have a measuring tool. You can click 2 points and draw a line between them. It'll tell you the distance.
So,
I had
is
never.
there any
And you can
other
make you can enclose an area,
discussion you had that
enclose
you think would be
a region, and it will tell you the
interesting
area
to share with the group?
in square miles, square kilometers, square meters, whatever you want.
Problem?
So we have to make a decision right now.
That'll be harder to bring to work from. How many people brought in the crossing?
Sorry, I did not realize that our talk was on.
How many people brought in the postage stamp? So actually we had about half and half. So is there anything else that you noticed about the algebraic thinking of your students that you thought was maybe something to understand why they thought that way, you thought was, you know, interesting to share?
This was a math student that was one time. She's actually a math graduate through couple. But she came up with an equation, and she came up with the fact that she got an answer that was a fraction, and it couldn't work because you couldn't have a part of the thing. You know, the example was something, you had to have open.
Right.
There's no combination of two stamps equals those values, so therefore they're impossible to make because it equals a decimal and stamps of the stamp.
Well, she actually came up with a formula for the postage stamps, and some of her answers were decimals, and she recognized that you can't have a fraction of a stamp.
And we kind of try to do like a simple equation, just one equation and decided to set a line for some numbers, and we just put in whatever number you wanted to try out. And
if it came up with a decimal, she knew it couldn't be made because it didn't get part of the stamp.
So she set up an equation with the two variables for the two denominations of stamps, something, and then she plugged in her own choice of values for like X or Y, or
And if it came up with, you know, a fraction there,
then she knew that it wasn't possible. So she actually came up with some kind of formula and tried to plug in things to it to realize which ones couldn't be made that way. Any other interesting work that your students did that you would like to share?
I noticed that we did the crossing the river. I did it for all of my classes across the board. About 120 students, and I would say more than 60% of them all started with picture, drawing how many, and a lot of them were able to make that connection of the portraits for the one adult and then the children child back. But out of them all, the one I showed you, I had just one student that could get down to the very back of that page and figure out exactly what the equations for any number of children and any number of adults.
Right.
All of them, just one, I mean, threw off that.
So yeah, on the crossing the river, there's that last page, which I don't know if I got that from anybody. Yeah, I guess this is the problem you're talking about. So you notice on this one they didn't fill anything out for question 4, and I think that's the question you're talking about.
Yes.
The rule for finding. I guess let me share that. So, and so you had 120. What grade level?
She's a sophomore. She's in the advanced placement algebra 2.
So do you have a bunch of grade levels out of those 120 students?
I only have one geometry class that takes in the juniors, but for the most part, they're all sophomores.
So you have 120. Some are juniors, most are sophomores,
Yes.
and only one of them got to question 4, or actually figured out how to do it.
Yeah, they weren't. The one that did was a sophomore.
And the one that figured out was a sophomore. Did anyone else notice something similar that people didn't get to the question 4 that did crossing the river?
I have you guys was understood what the pattern was, but they didn't know how to write it down because they were trying to explain it to me. They were saying, we know that it's an extra 2 trips for every kid past the second kid. So for like the third kid, you add 2 more trips. And just for the first 2, it's just that 1 trip. And so they kept trying to explain it, and I was like, well, just do the best that you can. And so I knew that they understood the pattern, they just didn't know how to write it down. And then I did have, I think it was like only 4 of my 35 kids that were able to actually write down an algebraic expression for it.
For problem 4 or for the original?
So for any number of adults and any number of kids.
So for this
But
problem?
they wrote, yeah, that it was 4 times the number of adults plus 2 times the number of children minus 3.
Okay.
And so, but I had a lot that were, and then there was some that were like, we just don't get it. So,
Right.
and then someone said you just do math differently. So I guess that could be interpreted.
See, I had students that would get all the all the answers, but could not come up with all the rules were wrong. Like maybe it made sense in their head, but paper is just not.
So they got, like, they calculated correctly if you had 5 adults and 2 children and things like that, and then they made a rule, but the rule doesn't fit even the ones that they figured out, or it doesn't fit in general?
It's written very weird, and even on the first one, they were using too many variables.
They're newcomers too, so.
Okay. Their transition from the concrete of what we're doing to writing it down.
And that's important, you know, that's a big step for a lot of people. So it sounds like a lot of people kind of understood the pattern, but they had a hard time formulating it mathematically or writing it down, which is pretty typical. So. Anyone else have something they'd like to share? So some evidence that they didn't understand what they were reading.
Because I was from nothing when I asked them to do. So either they weren't reading well or they didn't understand what they were reading.
Right. Okay. That's
There's a lot of ESL students.
okay. So, and there's quite a bit of reading in these kind of problems, and you have to understand the details in the reading too. So some people, it was evident they didn't understand the reading because they set up problems that were not anywhere similar to the reading at all. And did they do the crossing the river problem?
Yeah.
Yeah.
I found a video, about 3 minutes long, that showed a little boat, and it showed how many people would be in the boat. I mean, it was wicked. And so, because they were trying to put, you know, an adult in a show. They thought there always could be a big people. So finally I found this video and showed them.
And I know that there's an app there's apps for this too, Crossing the River apps, and they do a lot of different variations. They don't go to general, but they give you like 5 children and 4 adults and stuff like that, so you can actually figure it out. So I'm trying to do it with the least number of moves possible. And if you finish it, it tells you if you got to the minimum. You know, there's different apps. So yeah, I'm sure there's lots of videos too. Which this is an extremely famous problem. This goes to as general as you can get with any number of adults and any number of children. So the people that got to the final question, you know, this is as abstract as this problem gets. So most of the time you wouldn't, you know, you always would go to this because we're trying to promote algebraic thinking, right? But the actual problem itself is typically like the beginning part, right? Something like this, you have a certain number of adults and children and you're trying to figure it out for that specific example. But then jumping to the general is what algebra is all about, right? I mean, algebra is generalizing computation. That's what algebra is. Let's see. Okay. So, the next thing I'm going to pass out is just some thoughts about the way you can ask questions so that it promotes algebraic thinking rather than just a computation skill. Once you could read this, there's a last question at the end of this, which asks about, can you think of examples yourself that follow this kind of pattern? One of the examples in here is you could ask the Descartes and Euler problem as a completely computational problem, and then give that as an example. So later, just give me some examples of problems that you have computationally, and then how you could ask them to go about breaking. So I'm going to pull this up. And so for the remote people, we're going to look at this paperwork. Let's see. Let me pause the recording while I open this. So if you're watching this, everyone in our groups is reading through this little information about how you can ask a problem in different ways. One, just computational. Another, you can ask it to promote algebraic thinking. So if you want to pause and read this, I'm going to scroll down through it. I'm going to enlarge it. So, if you want to pause at any time when you need it to read it. So once you read through it, I want you at your table to come up with one example that you could take a computational problem and rewrite it to promote algebraic thinking. So I'll give you say 10 minutes to read it and then 10 more minutes to think about that question. So if you're watching this at home or if you're watching this remotely, read through this information in 10 minutes. And then answer the last question here. Or this last little paragraph. Examples you could change in your own task to elicit more algebraic thinking. I'm going to pause the recording now. I'm going to let the groups work. So if you're watching this at home, just read through that, pausing it where you need to, and then answer this question. And once again, when you're turning this in for remote, for people watching this later, so I can check for your attendance, all you need to turn in for this section is an example of your own task that you could rewrite to promote more algebraic thinking. Okay, so, really, if you read through this, it's a lot of examples of how you can take a problem and you can write it in a way that promotes algebraic thinking, right? And then even gave how you can write the cross and roller problem as an algebra problem without any words. It's kind of interesting to see that now that we've looked at that problem a lot. So, are there any examples that you'd like to share with the group of a problem that's computational? I wrote down one myself too. Of a problem that's computational that could be rewritten from without breaking. You can come up and write it on the board. You don't have to, you can say it, but it's easier. You can have the problem. I know that you guys have some because I went around and talked to them. You don't want to come on board, just say it. All right. Or I can start calling on the table. Okay, so let it go to the table. What was your problem? You don't have to write it if you don't want to. Say it. Or you can write it.
Okay, right here. Okay.
Well, in calculus, we start with anti-derivatives instead of just giving them the formula and teaching them how to compute. To start with giving them the derivative and asking what function has this for derivative. And then we go through several examples and ask them to.
So give me an example.
So like what function has a derivative equal to 2x? And all those things are working in pairs, and then they come up with different answers sometimes.
So this is the one that promotes algebraic thinking. The one that would be computational be what?
Would just be what the integral is.
Or what is the anti-derivative doing?
So instead of giving them a formula and asking them to play, so kind of feel.
So this is the introduction of calculus 2 in the backwards way, right? So you can tell them how to calculate anti-derivatives. Actually, what function has derivatives equal to? So 2. It's a really strange question, actually. So, so which way, so you were talking about, instead of writing that, then you were talking about f of x equals x squared, what is f prime of x? So, because integrals are the reverse process of derivatives, so doing the reverse process usually requires more algebraic thinking to start with. Okay. And then wording it this way, like you said, it's not just writing the integral sign, it's actually telling them what it is at the same time as they're doing the problem.
Well, as we go through several examples, then we start trying to build the rules of how to get integrate x to the half.
So this would be just the symbol, this would be writing in words, so you know what you're actually doing at the same time. Any other examples? And really, calculus is is an algebraic process once you understand it. So the calculus part is not.
I have one problem. What are the zeros of x squared minus 3x minus 40? Is the original problem?
What are the zeros of What was it?
X squared minus 3x minus 40. And then the altered problem would be what polynomial has x equals 4 and x equals 5 as solution. And then is the answer unique?
So, the original problem, the solution is 4 and 5. X equals 4 and 5 to solve, right? So I guess. But
8 and
8, so it's looking 8.
yeah, I just,
But you didn't link them together. So if you link them together, so the first one, the solutions are x equals 8 and 5. If you rewrite, so negative 8. Negative 85. If you rewrite the same exact problem to promote more algebraic thinking, you can ask them for the polynomial that has those solutions, and they would have to understand. You know, they could write it really quick. They could just write, if they understand it well, they could just write this, right? And they could multiply it out if you wanted it as a, a standard form of polynomial. But they would have to understand a lot more about what's going on in this question than they would in this question. This question, they can probably plug it in their calculator and press solve, or a lot of other methods. This one, they really have to understand what's going on, right? So it promotes a lot more algebraic thinking.
Yeah, I like that polynomial. Might use a multiply to by or trinomial. I like that polynomial.
and I was thinking with is the answer unique? You know, you can multiply by 2, and you can have a conversation about vertical stretches or all that different stuff.
So yeah, and they could realize that it's not.
Or if there's no restriction on the degree, then 2x minus 5 or whatever, and can make it.
Exactly, yeah, you could start changing this, and those would still be the solutions, right? So, there's a lot of discussion about, and uniqueness is an extremely important thing to think about in mathematics. Because if something's unique, you don't have to find any more. You're done, right? You can categorically define something. If it's not unique, you can't do that. So, in mathematics, the idea of uniqueness is sought after a lot. A lot of different kinds of problems. Okay, go ahead. Any others? I just thought of one actually thinking about the uniqueness, because you could say, what is the square root of 4, right? You could ask someone that, or you could say, what number when squared is equal to 4? And you could ask, is that unique? And your answer could be what? 2 or negative 2. And this could lead to the discussion that our square root function is a choice. You have to cut it to make it a function, right? Because it depends on where you're at. You can do inverses. You have the quadratic here, x squared. The square root function is half of the inverse, right? So you have to make a choice to make it a function, to make it pass the vertical test, and we generally choose the upper half, which is the positive answer. But that's a choice that we're making. It's not unique. And that leads to a lot of things in complex analysis. Okay, so the uniqueness made me think about that one. Any other algebraic, and you could take this off in a lot of different directions if you wanted. Any other? Let's do one more, please. Or maybe, and then if the group the remote group in Marfa, if you have one you'd like to share, you're welcome to chime in. I'm going to collect one more example, and then I have one that I wrote down too. Okay, do we have someone touching the wire?
Oh, I've not touched it before.
You don't have to touch the board, you touch the pen.
Oh, I touched it again. So I'm going to write down just a column on this thing.
So this is the stop for own discussion around recent classroom problems that could be improved in this way. Okay, that's good. And then the questions for mathematical thinking would be, what would you subtract from 3x squared plus 5x minus 2 to get minus x squared plus 7. So we're taking the same question, giving the answer in one piece of the question, and asking for the other piece, right? That the answer would be this, right? I would assume that's what you're doing. Keep assuming that. And so this does promote a lot of algebraic thinking if you think about it, because this would make them understand grouping of like terms. But if they don't understand grouping of like terms, they can't answer the second question. They can answer the first one just by thinking about patterns maybe and just doing up with these problems. But this one, they have to understand grouping of like terms before they can give you an answer. And that's an important idea in algebraic equations, right? So they would need to realize that I need to take this 3x and make it minus, so the only way I can take the 3 and make it minus 1 and subtract 4, right? And they have to understand that process pretty well before they can answer the second question. And they do have to kind of understand the first one, but not maybe as deeply. So, okay, and the other one I don't know. Let me see what they wrote over here. They wrote, we're back now. Okay, does your group, Warren, does your group have any of the examples, recent classroom problems that could be improved that you'd like to share with us? A way that you had a problem that you took and improved it?
Well, I asked for examples that came from recent classroom experience, and one of them, the first one that came up, was about logarithms and exponentials and the equivalent going back and forth between the two forms, which is sort of, that's where you get revealed that students really don't have the doing and undoing habit of mind, because logarithms elude a lot of students. And the other thing we were looking at was an example from geometry, developing the notion of the sum of the interior angles of a polygon, and then turning that problem around and taking a number and asking what, if any, sort of polygon could this be the interior angle sum for? So, given the angle sum, can you figure out how many sides the polygon had?
That's good. So that's working backwards on that problem.
Mm-hmm. Or given a number that doesn't actually correspond to a polygon, could you discover that, by the undoing process, that that it can't be the angle sum of a polygon? Right.
Those are interesting ways to change those problems. I like it. Do you have anything else to share, or if not, we'll probably move on to the golden apples problem.
That's cool. I think we're ready to move on to that.
Okay, so I'm gonna move on to that in our group here, and I'm going to pass it out over here, and then I'll pull it up digitally. So if you're watching this, I'm going to pause the recording for a minute while I pass this out. Okay, so if you're watching this at home, like I said before, on the last part, if you're either sharing on the Facebook page or emailing me a question that you could modify to promote more algebraic thinking, and now we're working on this, the following activity, the golden apples problem. So here's the activity. So I'm giving the groups here 25 minutes, so work on it for 25 minutes. I'm going to pause the recording, and so you can give yourself some time, 20 to 25 minutes, and then when you tune back in, we'll be discussing the solutions. Okay, so we are coming back from working on the golden apples problem. And now we're going to discuss the golden apples problem. So I'm going to pass out the golden apples discussion.
I got to see if we can answer it. Let's answer it first. So.
So you read the question. The prince picked some apples. He got stopped by 3 different trolls, and each time they asked him for half of his apples, but they had -2, and there were 2 more, right? And so when he finally got to the 3rd troll, he had 2 apples left. So how many did he start with? Anyone get a different answer? All right. So then the second question was, if the prince had 4 golden apples left when he went home, then how many apples had he picked? 4 left. Started with what? 60. And then it said if he had 5 left, he started with how many? And if he had 6 left, 76. And so then, from your answers to 1 and 2, you're supposed to predict how many apples he would have left if he started with, right. How many apples would he have started with if he came home with 20, right? Which was what? 188. Right. How did you solve number 3? How so? So you started with the 20, and you took 20 plus 2 and doubled it, and then added 2 and doubled it, and then added 2 and doubled it, and that's where you got the 188. Good. So did anyone do it a different way?
I thought it was the original number. Over 2 minus 2 is the original number.
So then you could have started with the original amount that you called X, and you take half of it minus 2. You start with X apples, the troll takes half of them minus 2 more, and you put the same thing. and that's equal to 20, right? So that's following the words directly, right? So this way you're thinking backwards. This way you're following directly, but you set up an algebraic equation, right? Which can be used in more generality, I guess, at this point. Both of them you can do each other. And so then you solve for x, and you find x is 188. Does anyone do it a different way than either of those methods?
Holy cow.
Yes, someone? Sounds like someone did it differently.
No, she did it.
What about
She did it like that right there. She did.
this way, right? Yes.
If you start with the number that you ended up with as your x, and your y would be the number you started with, the equation would be like 8x plus 28.
So 8x plus 28.
And the x is the number you ended up with, and y is the number you started with.
In this case, x is the number left, and y is the number started. So you actually you can set up an equation, right? And so this is used in general, not just for 20. Okay. And the other ways that it would solve. So then you plug in, I guess you plug in 20 for x here, and you would get the 188. Right? How did you get that equation?
A table.
So you made a table, and you realized it was a linear function because it increased by the same amount every time, went up by 8, and then 8. So it's a linear function, and you have 2 points. You can find any line. So that's one way you could have done it. So because you gathered information, and you could recognize it was a linear function and solve it that way. Now you could, in general, work this way too, right? You get the same equation. So if you, in general, I don't like to use x and y all the time, so I use A was the apples you start with, and L was the apples left. If I give my students a choice, they always pick x and y, no matter what the problem says. So sometimes I let them pick, sometimes I don't. But if you wrote this out in the way that Ray has talked about, you could, you started with A apple, so you take half of what you started with minus 2, half of that minus 2, half of that minus 2 is equal to L, right? Now, of course, the other way works faster, but this is how I thought about it, because I just wrote down the word as I read the words, right? If you multiply this out, if you take the 2 and brought it to the side and multiply by the 2 to get rid of the half here, you'd be left with half A minus 2 minus 2. The 2 went to the other side, so you have L plus 2 multiplied by 2 is 2L plus 4. Okay. Bring this to the other side, you have 6, and multiply by 2 again, you have half A minus 2 equals 4L plus 12. Bring this to the other side, you have 14, and double it, you have A is 8L plus 28. That's the same equation, right? So y equals 8x plus 28. And so you can solve this now in general completely. So I asked some people that finished early, what would the question look like if it was just computation, if it was not promoting algebraic thinking? So does anyone tell me that? Because some people finished early. So we've been, in the last paper we looked at some problems that were both written as computational and written to promote algebraic thinking. So this problem promotes algebraic thinking. How could you write it to just be a computation?
given that the x equals ax plus 28 times f of 20.
It's the same problem. Right? Just all you have to know is the formula and plug it in this version of the problem. Right? In the word problem, you had to find the formula and then plug into the formula, right? Or actually, you didn't really have to find the formula. You could do it computationally, which I think probably some people did. Probably several people did that, because it doesn't say find the formula. It just says find it for 20. But if you look at what you did, find it for 20, and you didn't find a formula, you really found a formula to do this. So, okay. So I like this kind of problem personally. I think it's fun. But the next one we're going to look at is, again,
Chris, hello?
Yes.
I'm curious if anybody up there followed a strategy of guess and check.
What was that?
I'm curious if anyone up there followed a strategy of guess and check.
Did anyone follow a strategy of guess and check?
Anybody here follow a strategy of guess and check?
That's another way you can do
So, we had a really good discussion. We had a really good discussion the other night in my graduate course about how to answer parents who are concerned about calculators in the 8th grade STAR test. And the complaint that, oh, well, the kids can't do the arithmetic. And I think it brought up some points that really fit in here nicely. And so the problem is, you look at the symbols you were pushing around there, and the distributed property, and just lots of places for kids to make mistakes with pluses and minuses. And, throw in some fractions and life gets even worse. And so one of the things that came up was the 8th grade TEKS don't really talk about computation a whole lot. That those were instructional goals and things kids were supposed to master, in some cases several years earlier. And so one of the powerful things that technology allows you to do is something like this. That you can come in, well, actually, I did this a little bit backwards. You can come in here and create a table of values and do a scatter plot and look at different representations, and the technology allows you to move away from some of the computation. So you can go in and actually just, say, what happens if he starts out with 40 apples? What happens if he starts out with 24 apples? And generate some input-output pairs. And then look at the function that's there and see if you can come up with a rule from that. And see if you can then come up with a number that produces, say, in a table, once you've got something you think is a rule, you can go in and say, well, what leaves 4 apples? So you might try something like, what if I started with 36? And if I've got a rule I think is going to work, and it explains I've got some input-output pairs, I say, well, that doesn't leave 4 apples. So I might double that and try 72 and see what happens. And that doesn't even leave a whole number of apples. But this process of guessing and checking, that's actually more than 4, so my next guess ought to be a little bit less. And you can wind up validating your rule. There's really good algebraic thinking in there, but the technology allows you to not get lost in the computation.
Are you displaying something on your side? Because we don't see
Oh,
I didn't know if you were.
Goodness gracious, I'm not used to this. I was supposed to actually do this, and then...
I heard clicking, so I thought you were probably working.
Oh, good catch. Thank you. Yeah, I was doing this. So input-output pairs would lead me to come up with a rule, possibly, and I just had typed in the rule that does come up, and you might have gotten it the other way depending on which variable was the input and which was the output. The amount. This is actually, of course, starting with x being the number of apples that you start with, but moving over with the formula to the tabular representation. Once I've got a formula where I've generated a few input-output pairs by starting with a number of apples and figuring out how many are left by doing the process, Now I just have to go and see if I can stumble on one that gives me 4. Right? So I come in here and try, well, maybe 68 works. That gives me 5, so I got to try something less. And so kind of guess, check, and revise. And I'm still doing a lot of really good algebraic thinking in the process, but I'm not dealing with all those nested parentheses and trying to kind of, the arithmetic errors that are probably going to come from that. But I think the larger idea that came out of our conversation was that the technology can often allow you to address grade level TEKS with students whose computational skills are too weak to do that with paper and pencil exclusively. And that can lead to greater success at the higher level thinking that we're trying to pull from them. Anyway, you should have been there. It was a great discussion.
Sounds like it. Well, yeah, that's a good point. So, even if a student can't do the computation, you can still have them use the technology to think at the higher level, even if they would have gotten stuck.
Yes. No.
But there was a student I have who did very well in pre-calculus, but when he went to take his PSI to test into college, he couldn't pass the basic math and had to start with remedial portion for college.
Right.
So at one point, are we hurting them by not requiring the computation to handle the higher level math?
They are hurt by not having it, and it depends on the test. Some tests let you use a calculator, and some don't. So if they have to take a test that doesn't let them use a calculator, then they're going to be hurt pretty badly. If they can take a standardized test that lets them use a calculator and they were able to pass pre-calculus, they might pass into pre-calculus in college.
Well, and there are two thoughts there. One is if you've got kids that haven't learned basic arithmetic by the time they're in 7th and 8th and 9th grade, and you keep trying to teach that to them every year unsuccessfully, you never, ever get to grade level math. And I also have always fallen back on observing my own child. My younger child actually struggled with, and I don't think he mastered his addition facts till he was in pre-calculus. And he took AP Calculus and has gone on to great success. He got above 0 on the test. He made a 3, which isn't, awesome, but they don't just give that away. And he struggled with and never really mastered addition and multiplication facts, even up into high school. So there was in our own house an actual success that was facilitated largely by the integration of technology.
Definitely, and if they do take a test, I think, are you allowed to use a calculator on the SATs? I think you are. Yeah. So, at our school, if you do well enough on the SATs, you don't have to take some of the other tests, and you can pass into a class. Now, if you don't do well on the SATs, then you are required to take some of the other tests. And even if you get into a college, you could have a professor that doesn't let you use a calculator. So you could teach them how to search for a professor that lets them use calculators. And like Dr. Kep said, they could get to a place later where they figure, they learn those facts just because they're working on math problems that are above that level. They have to think about them, and hopefully eventually it'll stick, right?
I already had that problem, so I started questioning myself when that happened. If I make a mistake, I go teaching the higher level stuff and let them
No, I think, you kind of can throw both in, but not focus on, if you just focus on lower level math, you're going to lose them because they're not going to share.
So just out of curiosity here at UCTV, how many professors work there?
Calc 1, how many let them use calculators? It depends because we have adjuncts too. So
yeah, I actually require graphing calculators in my Calculus 1 and have for, since 2003.
I let them use a calculator up to a TI-84. I don't let them use above that. And they can't use their
Oh, amen. just one more thought, and then I'm going to shut up on this subject, is that when we talk about math proficiency and all that, one of the problems that, in hindsight, my own kid ran into is I learned very late in his academic career that he's very tactile and a kinesthetic learner. And almost no math teachers actually teach to that. They tend to try to emphasize symbolic orientations of, you know, here's a bunch of facts, here's a bunch of symbols, learn these facts. And that's not the way his brain actually works. He's got, you know, I would hold up his mathematical ability as being above average. I mean, like I say, he got through calculus and actually understood it and found calculus in college to be really slow because he had such a great high school teacher at OHS. But, you know, his issue was that he never really, his learning style was such that it didn't lend itself to the way most of the math teachers in the world teach math, because we tend to teach the way we learned. But our students don't learn the way we learned. If they did, they'd all be like us.
All right. So, are there any other comments or questions about that? All right. So the next thing we're going to look at, I guess the last thing we're going to look at, since we only have 30 minutes left, is this another example of thinking about writing problems that promote algebraic thinking. So I'm going to pull it up on the screen if you're watching digitally. I think it's right here. Yeah. And I'm going to pass these out for you guys to think about. So once again, it talked about how in that last paper you read had several examples of computational type problems that could be modified to promote algebraic thinking. Now you have the examples which we wrote down how it can be computational. So they're going to give you a computational problem and ask you to write it, a specific computational problem, to write it in a way that promotes algebraic thinking. I'm going to ask you about another problem. So I'll give you 15 minutes to work on this, and then we'll discuss some answers, and then we'll be done for the day. If you're watching remotely, think about these questions, and when you submit either on Facebook or email to me what you did when you watched this video, you can answer this last question. Question 3. I'm going to pause the recording now. So. Okay, so if you are watching this, we're coming back from the discussion, and we're going to answer these questions. So, who here has an answer to in what ways does the addition of questions to 2 and 3 accomplish the goal of eliciting more building rules to represent functions? So the original problem is the first question. Yes.
I guess for me, like, if I just had to put one to the brute force type thing, but then if they wanted more answers, I had to think about what would be a best way to do it.
Right, so you're basically asked to solve it in 5 different situations. So asking it once, sometimes you just go through the computation even if it's hard or complicated. But when you start asking more and more, then maybe it elicit the shortcut or some kind of formula, right? Any other?
It's the hardest when you have to have some kind of rule for it or a formula for it, then they really struggle.
Right. And it didn't ask them to find a rule, right?
No, they won't do. That first thing they say is, "There a math problem I can be involved in." And you say, "Well, it's not one."
Right.
I'm not reading algebraic thinking questions. instead of algebraic equation, we call it mechanical rule. And I think I like that better, that's not what it's theory. As you know, algebraic equation.
Right.
You come up with a mechanical rule that you want.
So they use the term mechanical rule instead of algebraic equation, so maybe that wouldn't increase the math anxiety as much. All right. What about the second? And in the group in Marfa, if you're discussing on your own, that's fine. But if you have anything to share at any time, you're welcome to chime in. The second one says, solve this typical pre-algebra question and discuss the question that follows. What is the problem asking students to do? Just evaluate, use substitution to plug into the function somehow, right?
Why is it so hard for them to substitute?
Well, I think they have a wrong notion of a lot of things. For some reason, they think this is multiplication. They don't understand function notation.
Even if you don't have a read like that, I mean, it is substituting. And it doesn't matter how operative I had that's what we were discussing earlier this week. Is
well, I think
taking out the M and the V. Take the M and the V out and put the plus and the minus stuff in there.
Well, I think one thing they don't understand is that those letters mean numbers, first of all. That it's a placeholder for numbers. I don't think they understand that. It's just a letter to them. And, you know, that's one difficulty.
I mean, I would say, look, if I'm not here, somebody's in my place. Somebody else comes and teaches you if I'm not here. Or if you're on the volleyball team and it's your person, it's your second string, your person comes out and that's substitution. You can't get them to connect.
Right.
Frustrating.
Yeah, it can be. But if you get them to the place where they understand that they will have grown a lot in their algebraic thinking. Because that's what algebra is taking computations and using letters or something to be a placeholder. So if they get that connection, that's the big step. What kind of algebraic thinking does it require? Basic computational, however you want to describe it, right? Once you understand that this means to replace the x with 5, which some people have a hard time understanding, you're just going through a computation. So in question 3, it refers back to what we did, right? We looked at questions that are computational and then the analogous question that promotes algebraic thinking. So did anyone come up with some interesting examples that make this computational question into a question that promotes algebraic thinking?
Could you use a basic area equation where the length is 2 more than the width? And the area is 5. Find the dimension.
So you're thinking about that. That's what I thought too was an area question. So, how would you like to word that?
A rectangle has where the length is 2 more than the width. The area is 5.
Has side length where 1 is 2 units longer than the other. And then what?
The area of the rectangle is 5 meters squared.
The area of the rectangle is say 35. What are the side lengths? So this would be the same question, right? But now they're having to think about creating the formula, but it's related to a real thing, a dimensions of the rectangle. So they have to know how to label the picture or draw it or a lot of different things. So this really is the same question, except we gave them the 35, which is the answer to the first one, right? And asked them to come up with the formula, basically, right? So any other? Yes.
I said, is there any number that you could use for X where you would get a negative value of G of X? Because the kids have such trouble with those things as -2, and the calculator is -4, -2 squared.
So you said, is there any number?
Is there any number for X where you'll get a negative answer for G? Or for G of X? Because when they put, -2 squared in the calculator, they forget the parentheses and they come up with -4. They don't realize how big it is.
Right.
And so we're thinking, they'll say, oh yeah, there's a whole bunch. Well, there's really only one -1. There's really only one.
So a whole number, I guess?
Yeah.
Yeah, there's only one whole number that you can plug into this function to give you a negative value out, and they could see that, and you could. Question could promote the graphical representation and a lot of other things, right? Oh, actually, it's this way. What is it? X times X plus 2, so it's this one, right? So the only solution is -1, right? You answer that question. So it takes the same function and asks a question that requires a little more thought or depth of thought. Any other?
Find two consecutive odd integers.
Find two consecutive odd integers. This product is 35. So this really, you get a similar thing, right? Because G of X is X times X plus 2 again. So consecutive odd integers would work here, right? Because the two numbers are separated by 2, and every consecutive odd integer is separated by 2. And so this one, you could use in a lot of different levels too, because they could actually figure this out without knowing a lot of stuff. They could just guess and check. But then you can use it and ask them more questions if that's what they did to promote some algebraic thinking as well. So they could guess. And if they understood prime numbers, they could factor it, which is an important concept too, and realize that 35 is 5 times 7, those are consecutive integers, right? So, any other interesting examples of using this problem, modifying it? And I thought about the area one too of, if you had a square room with a hall which is width 2 and has length the same as the width of the room, so you create this idea of a square room with a hall that has width 2, and you want to know how much carpet you need to cover the room or something like that, you could come up with that area question. Worded a little different because it's not just a rectangle, it's two kind of shapes.
The volume of the rectangle prison, yeah, the width is that. The length is twice the width.
So the volume
and the height should be 4 times.
of a rectangular solid or something?
The height is 4 times the width. Volume is 216.
216, where the height
is 4
There's 4 times the width, and the what length is twice the width? Right.
There's the area.
So you're creating x times x plus, well, I guess actually 4 times. So you create this shape here, right?
4x, x times 4x times 2x.
2x times 4x. So a similar kind of function, the multiplication of monomials or something, but it's related to the volume. So I guess we'll stop there today. And our next meeting is March 19th, right? And then the one after that is April 9th. And the one after that is May 7th, I believe. And the summer dates are set now. It is July 18th through the 22nd. So the summer dates are July 18th through the 22nd. It's that week. May, it's the first Saturday of May, so May 7th. And I sent an email out that has those on it. And I'll continue to send them. When I remind you, I'll say the remaining dates are. But the summer is July 18th through the 22nd. What? May 7th. So the remaining dates. We have none in June, and then a week in July, and that's the end of this grant. Yeah, so the homework is to go on to the WTMathEd.org, watch the introduction video, which is at the very bottom, and watch the introduction to the Inspire and Devices video. So those two, which is like 25 minutes total. With Jared Despaigne. And he will be here in the summer too. So, Jared, he lives in Utah now. Yeah, it's May 7th. May not week is before open Saturday. I'll do one session. Alright, that's probably fine because people can make it up.